this one here, the sigma star, is the set of all finite sequences. It's okay if there is the empty sequences there. When I put omega, it's going to be the set of all infinite sequences. And when I do the union of them, I will put infinity there, and the set of all sequences, finite or infinite. Okay, and then have some operations on sequences. We can do concatenation. So here we just take two sequences and we glue them together. And more frequently, we're going to do this merging operation, where essentially we glue two sequences together, but there is a common state in between that is not repeated. Yeah. And yeah, I will do the same when I have sets of sequences. I will just use the same symbol for sets of sequences. Good. So once I do that, then I can define my prefix trace matrix. So this is going to be essentially all the traces. So when I say traces, it means that they follow the transition relation. So they're the sequences of states, but they're all connected by the transitions of the program. So they're not just gluing states together. We're just actually following what the program does. They have a length greater or equal to 0, so they can be the empty sequence. And they all start from a set of initial states. So we have our set of initial states, and then we build all the executions that we can build from there. So here, this one is, again, our state I, from our example. The whole sequence here, so the states and the transitions, this is one trace, for instance. But, so we have that one trace, but we have also all the prefixes of that trace. We can basically, anything that starts from the initial set of states, and anything that follows from there. Okay, so now we define it again as a fixed point. I will tell you in a second why I keep insisting on these fixed points. It will come in a moment. Again, we start with the empty set. We go with the subset inclusion, but now we're building sequences. So now we are, instead of just collecting states, we're going to merge whatever sequences we have built so far with the next transition in the program. As a smaller example than the one that we have seen, for instance, we have this one. We have these three states. These arrows show the transitions between the states. And let's say that A is my first initial state. So now my iterations start with the empty set. The first iteration is just the empty set. Then the next iteration, I will add the states I to nothing. Next iteration, I will have again I there, plus whatever states I had in there, plus the transition. So whatever A I had before, I will add the transition AB. Next, I do the same. I go from A to AB, and from AB I can do one more B, ABB, or one BC, so ABC, and so on. So the fixed point, I don't do all the iterations, we cannot. The fixed point is going to be basically all the prefixes of the sequences. So an infinite number of B's, or an infinite or finite number of B's followed, no, actually, a finite number of B's followed by a C. In our example, it's going to be, well, we'll start with a state, and then we just keep adding whatever states we can reach to the sequences. Okay, so how is this prefix trace semantic related to the ones that we have seen before? They're related to this abstraction here. So we get to the actual, one of the important concepts in abstract interpretation. It's not the most important one, actually, but well, we have these Galois connections. Okay, so we have two partially ordered sets. We have an abstraction function that's called an upper adjoint, and a concretization function, lower adjoint. And the relationship that they have is this one here. So essentially, when we have an element, a complete element here, we abstract it. The abstract element Okay, sorry. So whenever we take an abstraction of an element, this one is smaller than an abstract element that is concretized as is bigger than this one. Essentially, how do I explain this? Well, okay. You take any two elements in this in these two sets. So this is called the concrete domain. Most of the time, this is the abstract domain. Sometimes you have a sequence of concrete domains before you get to the actual abstract domain, but it doesn't matter. If you take any two elements here, and you are in a situation where basically you abstract your concrete element, element C here, this one, the abstraction, will be smaller than your abstract element, and vice versa. When you concretize the abstract element, the concretization will be larger than the concrete element. So essentially, it's such that whatever abstraction you take is always going to be an over-approximation the same than the concrete element. I'll give you an example. This is one simple example here. We have two sets of integers here, ordered by subset inclusion. Here, we have the set pairs of basically numbers, plus minus infinity or plus infinity. So you can consider them as intervals or ranges or whatever. The order here is such that basically you have a range AB and a range CD. You have that their order, the partial order, requires the lower bound of the second element to be smaller. So essentially this interval, the second interval, is wider. You have a lower bound that is smaller and an upper bound that is larger than whatever range you have here. And now the abstraction function is going to take a set of integer. And so the set of integer could be, I don't know, 2, 4, for instance. When you do the range, you're going to do mean and max. So the mean is going to be 2, the max is going to be 4. And the concretization will just take all elements that are in between those elements. So between 2 and 4, you have 2, 3, and 4. And so you see that the set 2, 3, and 4 is larger with respect to subset inclusion than just set 2, 4. So this is. Okay, so between our prefix prefix trace semantics and our forward reachable abstraction, we have a Galois connection. So if we have a state in the forward reachability semantics, we have a partial trace that ends in that state in the prefix trace semantics. So essentially, the abstraction is going to take whatever sequence we have in here, or whatever trace we have in here. We take the last state, it's going to be our set of states here. And for the concretization, we just take whatever state we have here, and we build a sequence that ends in that state. Okay, and this is the approximation order that I was mentioning earlier. So this is an order that is not necessarily the same as the order that we use to build the fixed point semantics in each of those sets. In this case, it's the same, but you will see later on we have examples where the Galois connection uses one order in the two posits, but the order in which the fixed point is built is different. Okay?
Yeah. So this is telling us that if we have a sequence of states that's like a prefix, we can turn that into just the last state in that sequence.
Yeah, that's actually, yeah.
And how do we order the sequences of states?
Here we actually have sets of sequences, so they're ordered by set inclusion.
Okay.
We don't order sequences alone. Okay, so I need to dive a little bit more into order theorem. I will tell you what total orders are, because I need to define other notions. So total orders, we have, it's an order that is a partial order plus its total. So essentially, it's a partial order between all elements, so we can order all elements in the set. Okay, so when we have a partial order set, if we take the subset that is totally ordered, then this one is called a chain. And then we can define a complete partial order when every chain has a list upper bound. That's the definition of complete partial order. So whenever we take a totally ordered subset of the set, we have a list upper bound. The list upper bound doesn't always exist. Okay, and then I have to define the properties of functions that I need, and then I'll define the theorem that we have to use to transfer one fixed point definition into another. Functions. So we have functions that are monotonic if they preserve the order between elements. So we have two posits in different orders. If they are two elements of order, respect the order of the first posit. When we apply the function, they should maintain the same order. We say continuous, or Scott continuous in particular, when we preserve the list upper bounds of each chain in the first posit. So if we have a list upper bound, this one here, we apply the function, then we obtain the list upper bound of the elements after we apply the function. Okay. Okay, with all that, we have all the elements to define our fixed point transfer theorem. So this one allows, when you have a fixed point definition, I will show you the instance in a second, to transfer it into a different posit. So we have two posits, C and A. Well, in this particular case, actually, there are two versions of the fixed point transfer theorem. This one requires complete partial orders. That's why I had to define it, the partial orders. There is another fixed point transfer theorem that works also with the partial orders, partially ordered set. But yeah, this one is more complicated. So we use this one. We need complete partial orders. We need monotonic functions between them. And we need an abstraction function. We don't necessarily need a concretization function. We need at least an abstraction function. And we need this one to be a Scott continuous abstraction function. And we also needed to satisfy this commutation condition, we call it. So essentially, whenever we apply, we take the first function in the first posit, we apply the abstraction. It's the same thing as doing the abstraction first and then applying the abstraction function. Okay, if we do that, then the fixed point of f in the first posit, if we do its abstraction, we're going to obtain the fixed point in the second posit. So here is how we use it. So we have our prefix trace semantics that we defined a moment ago. Here we're building all the sequences starting from a set of initial states. Here we have our forward reachability semantics. We have our set of initial states and we build all the states that we can reach from it. We have our Galois connection. In particular, we have this abstraction that maps a set of sequences to the states that we find on those sequences. So how we apply the theorem? Well, first we have these two. These two are complete partial orders. These two functions, fp and fr, are monotonic. This abstraction and the two functions, they satisfy the commutation condition. And we have that this is Scott continuous. Actually, this one is an exercise for you to prove it this evening if you want, after the baseball game. Or before, if you have the time, let's see. So with all that, we have all the hypotheses of the theorem. So essentially, we can basically say, okay, the abstraction of my fixed point, which is, it's the fixed point of this other one. And this fixed point here is my R, here. And this one, this fixed point here is my prefix trace semantics, to which I apply my abstraction. So basically, I'm saying that this forward reachability semantics is an abstraction of my prefix trace semantics. Good. Yeah.
What makes one an abstraction of the other, not the other way around? Is it because one of them is like bigger, or is it kind of a?
There is just less information here. In a way, here you're keeping the transitions between states. Here you're just englobing all the states together, grouping them all together. So that in a way, it's more natural to see it this way. You could see it the other way around also. In a way, I think, yeah, that is. With respect to what the program is doing, you're keeping less information. Okay, I'll try to go a bit faster because otherwise we don't have the time. Okay, We can do the same backwards, so we can do the suffix trace semantics in a similar way. Starting from a set of final states, we can build all the sequences of, well, all the suffixes essentially. And similarly, we can do the fixed point definition as before. In the example, for instance, here, same example as before, we start with a C, and now we go backwards. So the first iteration is the empty set as before. Now the first iteration will add the final state here, and then we go back. You see, you prepend one position, so you have BC, and here you have C, BC, and B, BC, so many B's before the C, or you go all the way to the beginning and you do one B and so the fixed point is the same. Well, not the same, actually. You have all the suffixes that end in C. Yeah, for example, obviously works in the same way. For the abstraction, it works a bit in a similar way, but now, since we're going backwards, the states are the ones from which the suffix traces are starting, not ending, and vice versa here. When you do the concretization, you start from the states that are reachable, and you build all the sequences that start from there. Okay, you can again apply the fixed point transfer. Now this time, as an exercise, you prove this one instead of this one, and you also apply the theorem like this. Okay, let's see if I can do the other two at least. Okay, so now we have done prefixes and suffixes starting from set of traces. We can actually just build traces from wherever we want, not just from a specific state. And so this is what this partial finite trace semantic is building, essentially. So these are partial finite program traces. So essentially, pieces of traces so you have sequences of states where each state is connected by the transition relation, but they don't necessarily start from any particular state. So in the example here, they could start wherever in the middle, they can start from some other state, and so on. So here we can do the fixed point formulation in two different ways, actually. We can do it forward or backwards. It's similar as before. If we go forward, we start from whatever, the whole set of states, and we just continue from those set of states. And here backwards, we start with all set of states, and we continue from that backwards. In the example, for instance, to show you the difference, there isn't a particular difference actually. So the first iteration is the empty set. In the forward case, at the next iteration we get ABC, all the set of states. Here we get ABC. It's just the order in which you discover the partial finite traces that is different. So here, for instance, from A, you continue to AB. From B, you continue to BB or BC. And from C, you don't continue anywhere because that's the end of the state. And here you go backwards. So from C, you continue to BC. Yes, from B, you go backwards. So you have AB or BB. And from A, you don't go backwards to anywhere. And so on. And the fixed point is the same for both of them. Okay, for the abstraction, I will save you the pain of doing the fixed point transfer again. But it works in the same way. We just define the abstractions like this. So essentially here, we just have to, for the abstraction, we just have to put an initial state where we want to start from. So essentially we take whatever state traces we have, all the set of traces, and we take only those that start from an particular set of initial states, I. And for the suffixes, it's similar, except that we start. We want all the traces that end in a particular set of finite states. So here, it's a concatenation of the initial set of states followed by whatever sequence of states. And here is whatever sequence of states followed by a finite set of traces. And we do the intersection because we keep only those starting or ending where we want. Okay, good. Then finally, the maximal trace semantics, the most important one, actually, in this whole hierarchy. So this is the set of all finite program traces and all infinite program traces. So we have the finite traces, they end in what we call the blocking states, so the states that have no successor in the transition relation. So these are, we call them maximal because they're the ones that really end in the final states. They don't stop in the middle, there are no prefixes or so on. And we have all the infinite ones. So all the infinite traces that are connected by the transition relation. Let's see, 1 second, I want to see. Okay. Okay, now I want to give you a fixed point definition of this as well, but it's a bit more complicated than the other ones because of this part, because we have all the infinite traces in the between. So for this one, we actually have to define lattices first, and then complete lattices afterwards. So lattice is still a posit, but we have a least upper bound and the greatest lower bound for every pair of elements. So this is just a lattice. When it's complete, the lattice is when all subsets of the set have a least upper bound and the greatest lower bound. Which means that we have a list element and we have a greatest element, the bottom and top. So as an example, this is a very important example, we can take, for instance, the power set of all sequences of states, as an order. We can take this one. This order basically uses subset inclusion for the finite traces and the reverse subset inclusion for the infinite traces. And then we have, these operations are the meet and join the least upper bound and greatest lower bound. So the least upper bound will do the union for the finite traces and the intersection for the infinite traces. And vice versa for the greatest lower bound. You have the intersection here and the union here. And now in this complete lattice here, we can actually define the least fixed point definition of the maximal trace semantics. And you see here the starting point is going to be the set of all infinite sequences of states. This is very important. Basically, we take all the infinite sequences of states. This is our starting point. And then we do this operation here where we start by adding all the the blocking states, the states that go nowhere in the transition system, and we start prepending transitions to those. I'll show you an example what it looks like. But essentially we start with here. So here we are taking whatever sequences of states we want. And by doing this operation here, so you see this prepending is done also on this. By doing this, we are essentially doing a sort of a selection of the infinite sequences. We want all the infinite sequences that will satisfy the transition relation one by one, one step by step. So I'll show you. Okay, we start with the all infinite sequences. Here, we add the blocking state, C, and for the other ones, the infinite sequences, you see we are prepending all the transitions, so we have AB, BB, BC, and the rest. And this is actually a smaller set than this one, because we're only keeping the sequences that start with this transition. So we are reducing the set of infinite sequences, and we are making the set of finite sequences bigger, or finite traces. At the next iteration, we make this one larger, we prepend one transition, and we make this one even smaller, because now we are forcing the beginning of these infinite sequences to start with ABB, BBB, or ABC, or BBC. Nothing else is allowed. One more. Here, we keep adding C, so we keep prepending transitions, so we get BC, BBC, ABC, going backwards. Here we are adding even more transitions, restricting even more the sequences that we have here. So essentially, this set of infinite sequences of states is getting constrained more and more, because the order is this one. The more, show you here, the order of the executions is making the the finite trace is bigger and the infinite trace is smaller. Yeah.
Just a quick question on the next slide.
Yes.
The sigma omega is sort of all states regardless of whether or not they're reasonable?
Yeah, yeah.
Okay, so it's
yeah.
just any state of any kind.
Yes.
Yeah,
Any state, any sequence, so they don't have to be connected by the transition relation. In 3D sequences, they're not traces. And that is the point exactly. So here they have no connection, and here we are forcing the connection. We are forcing them at the beginning, and then at the second iteration, in the first transition, the first two transitions, first three transitions, and at the limit, all transitions will have to satisfy the transition relation, and they can be infinite. So this is a sort of a co-inductive definition, if you're familiar with that. And this one is an inductive definition. So we are combining essentially the two kind of definitions together. Okay, I have a whole denotational formulation, but we don't need to go through it. It doesn't matter. Okay. Yeah, okay. This one is a little property of Galois connections. Essentially, if you have one of the adjoints, you can uniquely define the other ones. So, for instance, if you have the gamma, you can define the alpha, and if you have the alpha, you can define the alpha. So here, how do I get from the partial finite traces to the, from the maximal trace semantics to the partial finite traces? Through these two abstractions. First of all, I have to get all the prefixes of the traces. So here, actually in my maximal trace semantics, I have all the suffixes, but I have no prefixes. So essentially I have to complete my set of traces by adding all the prefixes, and then I just throw away the ones that are incomplete. I just only keep the finite ones. Okay, and as an exercise, you can derive gamma from this alpha here. Okay, so we're done with this hierarchy of semantics. This is sort of what we, a bit of summary of what we've seen. So we have the most general starting point is this maximal trace semantics, and then all the other ones, you lose some information along the way. And depending on the property, we will see in a moment, the property that we care about, we can stop at any point in this hierarchy. If you want to know about the hierarchy of semantics and see more hierarchy of semantics, you can look at this paper here. Okay, finally, we get to the properties then. So here, as I said, we go up or down in this hierarchy depending on the property of interest. And there are different kinds of properties. The simplest one are the state properties. So essentially, I'm going to define properties by extension. So essentially, a property is going to be the set of elements that have that property. So a property of states is going to be a set of states. So states are sigma, and my set of states is going to be a property. So for instance, in here, this is an example of a state property. I'm going to say these are the set of my states, and R in that state is always greater or equal than 0. This is an example of a state property. When you have a state property, to verify it, you can just stay at the top of the iceberg, and you can use reachable state semantics or backward reachable state semantics and see whatever the states you can reach, they are included in the set of states that you want. This is how you verify the property. A bit more complicated are the trace properties. These are properties of executions. Examples are, for instance, termination is a classic one. Properties of executions are going to be the set of traces that are finite. So this is the definition of termination. Non-termination is the set of sequences that never terminate, so the infinite ones. And actually, any state property can be turned into a trace property just by basically taking the state and concatenating them in an infinite sequence. In the general case, the verification of trace property has to happen here at the bottom. You have to check that your maximal trace semantics is included in the set of states on your property that you want. There are some kinds of trace properties that are simpler. For instance, the safety properties. So these are the properties that specify that nothing bad ever happens. So any state property is a safety property, for instance. So here you can actually work with the prefixes. You can do exhaustive testing if you want. And you can falsify the property, but just by finding a finite execution that violates your property. So if you can find the prefix, which is a counter example to your property, you know that the property doesn't hold. Slightly more complicated are the liveness properties. Termination is one. Here you cannot verify them by testing. You cannot test if your program terminates. And to falsify the property, you need to find an infinite execution that doesn't satisfy the property. Okay, and finally, the more general case is what we call program properties. Some call them hyperproperties. These are sets of executions. So, for instance, saying that your program is deterministic is an example. Deterministic means that basically all your executions are singletons. You have one possible execution, and that's it. And how you verify this is actually you have to go, in the general case, you have to go to this collecting semantics. So it's the set containing your maximal address semantics. This is called the strongest property of your program. It's always, I always found it very confusing. I never could understand what the hell it meant. So I have an intuition for you. So, you consider a property, so as I said, we define a property by extension. It's going to be the set of elements that have the property. So now, what is Z? Who wants to answer? It's a set containing? Yes. It's a singleton set containing Z. There are no other people that can satisfy this property. This is her. She's unique. The only set that satisfies, the only set that is that property, that is her, is the set containing her. So it's the same for a program. So what is the property of being a program P? Well, it's a set that contains the program P, or actually its semantics, if you want. So this is the intuition for the collecting semantics. So here you have basically, went too far, sorry. The strongest property of your program, and you want that property of your program to be a subset of the property that you want to verify. Or another way, you want your program to have that property. Okay. Good. Okay, we can start the next bit and then we'll take a break. Okay, so as I said, this is a hierarchy of mathematical objects. None of them are computable. Okay, we cannot do anything with them. We cannot do any verification actually. And that's why we need to do the abstractions. And this is where we do the over-rounding up of the prices. So as a simple starting point, we're going to do an abstract state semantics or abstract forward reachable semantics. So this is going to be this element here. So we will over-approximate the set of states that we can reach in a program. So we will not compute this reachable state, but we're going to compute an over-approximation. Okay, I have a denotation of formulation, but I wasn't there. Yes, okay. So, in particular, well, for the sequences, it's going to be the same. Essentially, we're going to